You probably know what this is, and what this is, everyone's favorite metal, gold. The 79th element in the periodic table and used in almost every application in the world. But what if I tell you this right here is also gold? Because if we zoom in and look at the atomic structure, they're made out of colloidal gold nanoparticles, which is a nanoparticle of gold that is created by reducing a gold salt solution like chloruric acid to its neutral gold atoms, where the particles are suspended in a medium of gas or liquid. Then depending on the concentration determines the size of the particle. The creation and discovery of colloidal gold nanoparticles was by a man named Michael Faraday, a well-praiseworthy scientist who pioneered experimental work in the fields of electromagnetism and electrochemistry, where in 1857 Michael Faraday described the findings of fine particles, which were formed as a result of the chemical reduction of gold chloride molecules by phosphorus atoms. The reaction gave birth to freshly formed gold nanoparticles, which he called finely divided gold, as the term nanoparticle did not exist during his time. Since gold nanoparticles have such high surface energy, they naturally want to clump up together. This is where Michael Faraday thought of using a stabilizer solvent, any non-polar molecule that can absorb onto the gold surface, forming a protective layer that prevents it from oxidizing. Nevertheless, the first structurally gold cluster was synthesized 150 years later by Kornberg, of a structure of gold with over 100 atoms of gold. But before we talk about the applications of colloidal gold nanoparticles, we first have to understand the structure of them. The size of colloidal gold nanoparticles typically range from 1 to 100 nanometers, and at this scale they show very unique properties that are vastly different from their solid form. At the center of gold nanoparticles is a metallic core of just gold atoms, where the number of atoms determines the size and shape of the particle. The chemical composition of colloidal gold nanoparticles consists of gold atoms arranged in the form of their solid counterpart of a face-centered cubic, or FCC for short, in a crystal lattice structure, with one main difference. In solid gold, atoms are positioned at each of the cube's 8 corners and at the center of all 6 faces within the cube, which give effects to its tightly packed structure as each atom is in contact with 12 other atoms, which reduces the space within the center, allowing gold atoms to be stable. However, in colloidal gold nanoparticles, most of the gold atoms that are present are found on the surface of the structure, and with fewer overall atoms, this causes the structure of the atoms to be only surrounded by only 6 to 7 atoms depending on the size. This results in higher surface to volume ratio, which makes gold nanoparticles very reactive. Gold nanoparticles can also vary in shape depending on the size of their centers, which allows them to fit into many different applications. The main shape that colloidal gold nanoparticles take on is spherical, as it's the most stable with the lowest volume to surface area ratio possible. However, scientists can synthesize other shapes as well, such as rods, stars, triangles, cubics, and octahedrons with their own applications, which expand the uses of gold nanoparticles drastically. The intermolecular bonding within colloidal particles, such as colloidal gold nanoparticles, is the weak attractive force between colloidal particles and the medium they are present in. In other words, these are the London dispersion forces, where electrons shift to one side, creating a momentary dipole and attracting these particles together. As well, the electrostatic forces between the gold atoms also play a part in the attraction between these particles. However, the special properties of gold happen when they are bonded with a stabilizer solvent. Colloidal gold nanoparticles can form covalent bonds with specific stabilizer solvents, and even form hydrogen bonds that prevent them from being highly reactive, which makes them very applicable to medical applications, especially applications within the medical diagnostic field in medicine, which will be the focus of in this video. But to get a clear visual of a colloidal gold nanoparticle, here's a 3D model of it in the real world. This 3D model is an open structure of a colloidal gold nanoparticle, where the inner orange balls represent the tightly packed structure of gold atoms within the center, and the yellow balls represent the gold atoms on the surface layer that are spread out evenly. In the core, the gold atoms are connected with 6 other atoms through the electrostatic forces that form the basis of their lattice cubic structure. Then the pipe cleaners represent the stabilizer solvents that give nanoparticles their ability to bond using London dispersion forces, and hydrogen bonds through binding with the right molecule, which give effects to its special properties and ability to be used in medical applications. But what are those special properties? Colloidal gold nanoparticles have 4 main properties that make them very useful and applicable in medical diagnostic applications. One being their high surface area. The nanoparticle of colloidal gold is special as the surface area of the particle is relatively large compared to the volume of the particle. This results in a high surface area as there are more areas where reactions can occur. This causes colloidal gold to be highly reactive in its base form, which helps it with its application to bind with other elements like an antibody that allows it to be used in biological uses. Colloidal gold has a special ability to change colors into red, purple, blue based on the shape and size. This effect is caused by surface plasmon resonance effects, where in gold nanoparticle cores, electrons have a conduction band at different energy levels, with different temperatures and different thermal energies. An electron in these bands can freely roam around the center. However, they can absorb photons that excite these electrons, and by simply the size of the particle determines what wavelength of light is absorbed and re-emitted, which allows for the different colors of nanoparticles we can see. Colloidal gold can act as a catalyst during reactions, which makes reactions occur faster without changing the products at the end. This property makes gold nanoparticles very useful in medical applications. Gold nanoparticles have this ability as mentioned before because of their high surface area, which allows for more sites of reactions to occur, causing reactions to occur more frequently, thus allowing catalytic properties. Colloidal gold nanoparticles, despite being metals, do not have a little bit of toxicity towards human cells. Compared to other metal nanoparticles, gold is definitely the safest, making it suitable for medical application, as scientists can also alter the surface of these particles, making them less reactive, and since gold does not have any toxic ions, gold is a safe metal that can be inside our bodies if altered properly. Which brings us to the safety of these particles. Colloidal gold nanoparticles are generally known for their safe uses and relative non-toxicity towards living organisms. However, colloidal gold nanoparticles must be prepared safely to minimize potential harm when used in applications. The preparation calls for using distilled water, which should be distilled twice or even tripled, since colloidal gold is very reactive, so even the tiniest bit of minerals in water can set off massive reactions. The glassware used should be cleaned by undergoing acid passivation and thoroughly rinsed with distilled water. Colloidal gold nanoparticles can be preserved for a long time, but to prevent bacteria from growing or the agglomeration of particles, they must be kept in a centrifuge and at a steady temperature of around 4 degrees Celsius to ensure they can be safely used for later usages. Furthermore, in uses in medical treatment, the size of nanoparticles has been restricted to a length greater than 50 micrometers and a diameter of less than 3 micrometers to ensure that it can be removed in later usage through the gas exchange process. So what does it all mean? The properties and structure of colloidal gold nanoparticles have amazing applications that could significantly impact many applications. Like mentioned before, the use of colloidal gold nanoparticles in medical diagnostics has revolutionized how we identify and treat for early detection of new diseases. The first use of gold nanoparticles in medical diagnostics occurred in 1971, by which researchers Falk and Taylor used gold nanoparticles in biomarkers for microscopic visualization of the surface antigens of the Salmonella family of bacteria. Since then, gold nanoparticles have been used everywhere to detect viruses within the human body, from early detection of cancers, heart disease, and Alzheimer's disease, to pregnancy tests and rapid COVID-19 tests. And according to research at Russia's National University of Science and Technology, Alexander Opsy explained how the use of colloidal gold nanoparticles in medical diagnostics has increased the detection limit of analyzed substances in biological fluids. Now let's talk about some real treatments and application that utilize the power of colloidal gold nanoparticles are firstly in lateral flow assays, which are rapid, cheap, and quick tests that anyone can use effectively to see if they are positive for what they are testing. The way colloidal gold nanoparticles are used in these tests is that they are conjugated, or infused with detection antibodies that when applied to a sample, usually blood, saliva, or urine, can target the specific antigen that the particle was infused with. Then these particles accumulate at the test line and mark if the specific antigen is present. This allows for quick results that are virtually harmless to your body. For example, in pregnancy tests, the nanoparticles are infused with anti-HCG antibodies, which can detect the HCG hormone within urine that is produced in a woman's body after the embryo implants, and then marking it as a positive test if it's detected. Another diagnostic technology that uses colloidal gold nanoparticles is immunogold labeling, which is a technique used in electron microscopy where nanoparticles are linked to antibodies and they are able to pinpoint the location of specific antigens within the cell. They enable for high resolution visualization within the body that shows the different distribution of different proteins. This means that colloidal gold nanoparticles can be conjugated with substrates that can bind with the specific protein doctors want to detect, specifically from proteins that are made from tumor cells or other biological diseases that can prove a person has a diagnosis. They appear as black dots in transmission electron microscopes, clearly showing where the molecule is. For example, in the detection of breast cancer, the colloidal gold nanoparticles are infused with anti-HER2 antibodies that bind to the HER2 protein that is present on the cancer cell membrane. If bonded, the particles will signal the detection of this cancerous membrane on the electron microscopy by the visualization of black dots, which allows for quick action to be taken to help treat victims, which clearly show the impact they have on society. They have revolutionized the way people all around the world can access treatments and testing effectively. Firstly, colloidal gold nanoparticles have enabled many people around the world the ability to detect many diseases early, before they cause life-threatening damage. It gives these people a chance to diagnose themselves before serious effects take place. Furthermore, the development of rapid and affordable tests such as pregnancy tests allow women to empower themselves to privately test if they are pregnant or not without needing confirmation from anyone else, as well as help aid in mass screening such as COVID-19 testing around the world to help diagnose millions of people around the world. The quick and rapidness of these tests save major time for doctors and hospitals, which allow them to focus on more serious matters occurring. Also, the affordability of these tests will encourage more people to diagnose themselves, even if they didn't before, because of specific issues such as financial or insecurity issues of seeing a doctor and letting out their secrets. Nextly, the use of colloidal gold nanoparticles in medical diagnostic no longer requires the use of high-tech labs, electricity, or trained technicians for testing for new diseases. For example, people in rural areas can diagnose malaria in just 15 minutes with a single test without a hospital. Even more, colloidal gold nanoparticles allow for advanced cancer research and treatment that can target specific cells without harming a person's whole body. Specific treatments have been developed, for example, SCRS biosensors that can use colloidal gold nanoparticles to detect cancer biomarkers within your cells. Instead of the patient going through chemotherapy, doctors can administer colloidal gold nanoparticles in photothermal therapy or in drug therapy, where chemo can be delivered straight to the cancer cell itself without harming the rest of your body. However, the use of nanoparticles can also be used for the worse, as well as placing a false security on people's well-being. In rare circumstances, certain tests can give false securities for a person when the colloidal gold nanoparticles are improperly used. As well, it can be overused in areas where they are not specifically designed for. Places with not up-to-date healthcare can get false or non-scientific results that come up with a diagnosis on their own. This can significantly harm individuals if they're not careful, as the test they're using is not compatible with finding the disease that the user is trying to treat for. Furthermore, the power of colloidal gold nanoparticle is very unique in that theoretically, for military or governmental use, it can be functionalized for sinister activities. For example, in military use, gold nanoparticles can be used as trackers that travel through your bloodstream, which would make it basically impossible to detect or remove from oneself. This could lead to a new age of war where biological weapons are the advantage in war, which will eventually lead to the overall demise of all morality around the world. However, this is very speculative and not a real application that is possible at the moment. Additionally, colloidal gold nanoparticles pose a major threat if inhaled, since these particles are insoluble in polar solvents like water. This allows them to accumulate in the lungs indefinitely with no way of removing them, and as more accumulate, this increases the rate at which they can cross into the bloodstream and accumulate in other organs as well. Prolonged exposure will result in respiratory issues and neurological issues if accumulation takes place in the brain, which can lead to death if not treated. But what is the effect on the environment? Colloidal gold nanoparticles typically have very low risk, with no concerns towards environmental factors, as gold itself is a very stable element that does not contain any toxic ions compared to other metals. However, coating with specific surfactants can cause damage to specific organisms. Inland, there is no evidence of bioaccumulation of these particles, and the only reasonable threat is the disposal of billions of tests that leave plastic and other waste in landfills.